Here's example 5 of using the law of sines. So we want to solve triangle ABC given angle A is 35 degrees, little a is 12, and little b is 16, and we want to round to the nearest hundredth wherever appropriate. So we're just going to start this exactly like examples 3 and 4. So we're given two sides and one of the angles that's not in between these sides. So let's just go ahead and get started then. So again, we can't draw a picture yet because we don't have enough information to get an accurate picture of the triangle. So we're just going to say, okay, I have capital A, and little b, so let me use the law of sines to get capital B. So sine of b over little b equals sine of A over little a. So multiply both sides by little b, and I get sine of b equals little b sine A over A. We know little b, little a, and capital A, so let's just toss them into there, and we get sine of b equals 16. Okay, little b is 16, capital A is 35 degrees, and then little a is 12. Okay. Now, yes, we could reduce and simplify because there's a common factor of 4 that we can pull out, but it doesn't really matter because we're going to toss all this into a calculator anyway, so there's no point in giving ourselves an extra step. Now, what we want to do, just like in example 3, we want to make sure that this is actually a valid value, because eventually what's going to happen is we're going to have to say b is the inverse sine of 16 sine 35 degrees all over 12. Okay, that's one of the things that we have to do. There's actually something else also, but anyway, we'll talk about that later. But for now, we have to make sure that we can actually do this. Okay, because remember in example 3, we ran into that problem where we couldn't because this expression here was larger than 1. So basically, what we have to do is make sure that this is a legitimate value. So 16 sine 35 degrees over 12. Let's pull out our calculator and make sure that's okay. Okay, make sure that we're in the degree mode. So we're 16 sine 35 degrees divided by 12. And that's approximately 0.76476 and so on and so forth. Now, this is not, when we do the inverse sine, we don't want to take the inverse sine of this, but the reason that we just did this, okay, what I mean is we don't want to take the inverse sine of an approximation, we want to take the inverse sine of this exact expression there. But the reason that we just did that is because we want to make sure that this actually is something we can take the inverse sine of. And because it is smaller than 1, okay, we see there 0.7647, it's smaller than 1, so we can take the inverse sine of it. So it's okay to do this. That's all we're checking right now. Now, when we actually do the inverse sine, we want to toss it into the calculator just like this. Okay, we don't want to use this approximation, this decimal approximation. We don't want to round it or anything and use that. We just want to use this exact expression. And the reason is we want to minimize the numeric error here. So we want to minimize all the error as much as we can. So if we evaluate this and round it to a few decimal places, we're going to get a little bit of error, and we don't want to have that. If we can avoid it, definitely avoid it. And in this case, we can avoid it, so we will. Now, with that being said, there is one other thing we have to worry about, which we briefly mentioned in the last video. Now, when we say this, so let's come up here. Okay, so b equals the inverse sine of 16 sine 35 degrees over 12. So we have that. Inverse sine of 16 sine 35 degrees all over 12. Okay, but there's something else that we can do. Or there's something else that we have to check now. Or b equals 180 degrees minus this exact expression. 180 degrees minus the inverse sine of 16 sine 35 degrees. Yikes, all over 12. Really running out of room there. So b is this nasty expression here, or b is 180 degrees minus this exact same expression. Why is that? So we explained it briefly in the previous video, and we actually talked about it in more detail in an earlier video, but we'll talk about it again here in case you missed that earlier video, and just to be thorough here. Okay, so back here we said sine of b equals this big mess here. So when we say sine of b equals stuff, okay, Now, if we say B equals the inverse sine of stuff, then that's going to give us this angle right here. Okay, but remember from symmetry, so this is a unit circle right here, and when we take the sine of an angle here, so if this is our angle B, now the sine of B is the y-coordinate of this point here, but this point over here, also on the unit circle, has the same y-coordinate. Okay, so this could be this could also be angle B over here. Okay, but the inverse sine only gives us this one. So how do we get this one here? Well, notice this angle and this angle are exactly the same because of symmetry. So this angle here, they're exactly the same because of the symmetry. So since this is angle B, this is also the same angle B here. Okay, this angle right here is the inverse sine. This is the inverse sine of stuff. Okay, so this angle right here is going to be the exact same thing. This angle right here is the inverse sine of stuff. Okay, so sine of B equals stuff. This is inverse sine of stuff. This angle right here. This angle right here is exactly the same size and it goes in the same direction. So it's the inverse sine of stuff. So how do we get this angle right here? Well, if we go all the way around, that's 180 degrees. Then we'll subtract off this angle here. So 180 degrees minus this angle here gives us just this part. Okay, so 180 degrees minus this part right here, subtract this, and we'll just be left with this, which is what we want. Okay, so basically the other one is, so we say or B equals 180 degrees minus this angle, which is the same as this angle, which is the inverse sine of stuff. Okay, so again, it's really just, it's exactly the same thing that we talked about when we talked about solving trig equations, when we had stuff like sine of theta equals 0.67, things like that. It's really the exact same thing we talked about then. So just the key to keep in mind is symmetry. Because of the symmetry, there's a solution over here and a solution over here. And also because of the symmetry, this angle and this angle are exactly the same. So do pi radians or 180 degrees minus this angle right here, and you're just left with this. Okay. So that's why when we have this SSA case for the law of sines, when we have the SSA case, we always have to worry about this. Now in example 4, it didn't matter because in example 4, we ended up with 90 degrees. So 90 degrees or 180 degrees minus 90 degrees, but 180 minus 90 is 90, so you get the same thing twice. And in example 3, it didn't matter because there was no possible solution anyway. So this is another thing that could happen, is you might have these two possible cases here. Now it could be the case that they both give you a possible triangle, possible solution, or only one of them, only this one does. Okay, so it might be the case that this gives you an angle that's too large. So in this example, they'll actually both work out, but in the next example, we'll see what could happen if this doesn't. So a bunch of different cases to consider with the SSA case. So SSA could lead to a bunch of different things. No triangle, one right triangle, one more general triangle, or two triangles. So anyway, continuing with this. So now we have these two separate cases here, so let's keep them separated. So B equals the inverse sine of all this mess. Let's go ahead and continue with that. And again, we only did this part in the calculator to verify that this is actually something we could take the inverse sine of. Now that we know it is, let's go ahead and just do inverse sine of this expression, not the approximation. Be very careful about that. And we also wanted to do 180 minus that. Just make sure we're in degrees. So 49.8864. Okay, let's round out to 4. So we're supposed to round to the nearest hundredth in our final answer, but let's round out to 4 decimal places just for now, and we'll explain why later. So 49.8864 and 130.1136 okay, degrees. Okay, so this here, so B is approximately 49.8864 degrees. And here we get B is approximately 130.1136 degrees. Okay, Now, why do we round out to 4 decimal places? In the final answer, we only have to round out to the nearest hundredth. But what's going to happen is we're going to have to use these. So now we're actually doing 2 separate problems. So we have one case is b is this value, the other case is b is this value. And we're going to have to proceed each of these separately. But the reason we did 4 decimal places is because we have to use this value of b to get other stuff later. So what we're doing is we're using an approximation, which we want to avoid if we can, but now we cannot avoid it. So since we can't avoid it, we're going to give ourselves more decimal places than we need in the final answer. Because if we round out farther, then the error that we get from rounding off decreases. If we round out farther, then we'll be in better shape. So if you can avoid using an approximation, avoid it. If you can't avoid it, give yourself more decimal places so that you can minimize the errors that occur, okay, from rounding. Okay, so this is angle B. Now let's use angle B to get angle C. So kind of running out of space, and we've done it a bunch of times before, so we'll skip some of the details here, but basically the point is A plus B plus C equals 180 degrees. Okay, if you add up all 3 angles in a triangle, you have that. So using that fact, we have angle A, we have angle B. Angle A is 35 degrees, angle B is this mess here. So angle C is approximately, using this value of B, angle C is approximately equal to 95.1136 degrees. Okay. And again, we're keeping it out to 4 decimal places in case we have to use it for another value later. Okay, so now we have angle, so again, we just plugged A equals 35 degrees into here, B equals this mess into here, and then we just solve for C. Okay. So we've done it a bunch of times in the previous examples, and we are running out of space here. So anyway, and we'll do it again over here separately. We'll just one problem at a time. So now let's get little c. Little c is the only thing left. So if we want little c, then we'll just use the law of sines. So little c over sine of c equals, let's use little a over sine of big A. Because that way we can avoid using this B approximation. So we're going to have to use the C approximation, unfortunately, but we can avoid using the B approximation, which is nice. So this tells us that C equals A over sine A times sine of C. Okay, and we know what little a is. Okay, little a is what? Little a is 12. Big A is 35 degrees, so this is sine of 35 degrees. And then we're going to multiply that by sine of big C, which is this mess here. So this is going to be multiplied by sine of 95.1136 degrees. Okay. And then when we do that, what's going to happen? So we're going to get little c is approximately, and then since we're done with this case, we don't have to round out to 4 anymore. We can just round out to 2, because that's our final answer. Okay, so we're going to do (12) divided by the sine of 35 degrees, multiplied by the sine, oops, not the natural log, the sine of 95.1136 degrees. And we see that that's approximately equal to 20.84. 20.84. Okay. So C is about 20.84 here. So we'll put a box around that. Okay, so for that case we have C, little c is approximately 20.84. Big B is about 49.89. So big B is about 49.89 degrees. Okay, big B is about 49.89 degrees. And really running out of room here. Let's erase this stuff over here. Okay, so for that first case, little c is 20.84 approximately. Big B is approximately 49.89 degrees, and big C is approximately 95.11 degrees. Okay. So those are the answers for the first case. Now for the second case, we're going to do exactly the same thing, but with this other value of b. So let's erase all this stuff here. So we don't really need that anymore. So we're going to erase all this, and now we're going to do exactly what we just did with this case, but now we're going to do it with this value of b over here. Okay, so if b is approximately 130.1136 degrees, then we'll just go through the exact same thing. A plus b plus c equals 180 degrees. And here we have more room, so we can do a little more work here. 35 degrees plus 130.1136 degrees plus c equals 180 degrees. Okay. Now just solving this for c, so add these two together, and we'll get 165.1136 degrees plus c equals 180 degrees. Subtract this mess from both sides, and we get c is approximately equal to 14.8864 degrees. Okay. And again, we're keeping it out to 4 decimal places in case we have to use it to get another approximation or another answer later on. So, so that's big C. Now we have to get little c, and then that's it. So what we can do now is say, let's use a different color. We're getting kind of cramped in here again. Little c over sine of big C. Just like before, we'll say little a over sine of big A. Okay. So again, we're just doing exactly the same thing we did with this, but now we're using this value of b because there are two possible triangles here. Okay. So now c equals a over sine A times sine of big C. Okay, so little c equals little a is 12, and then big A is 35, so this is sine of 35 degrees. And then we're multiplying that by the sine of big C, which is this mess here, 14.8864 degrees, really running out of room there. So then C is approximately, so let's toss that into the calculator. So this is 12 over sine of 35 multiplied by the sine of 14.8864 degrees. And that's approximately 5.37-ish. If we round out to 2 decimals, 5.37. Okay, 5.37. So that's little c there. Okay, and then that's pretty much it for this example. So let's summarize all the results. So again, there are two possible cases here. So let's erase this. And we'll put our other triangle over here. So little c was approximately 5.37 in this case. Big B was approximately 130.1136 degrees. Actually, since we're doing the final answer, let's round to 2 now. 130.11 degrees. And big C is approximately 14.89 degrees. Okay, so quite a mess there. It's not as bad as it might have seemed from the video. It just it takes a lot of time to explain everything and go through it. But really, all we're doing is just using the law of sines and remembering we have to do this. And then if this actually works out, if it gives us some valid values, then we have to go through 2 separate cases, and we'll get 2 separate triangles. So notice this triangle is well, actually, I guess they're both obtuse. But anyway, what are these triangles going to look like? So if we were to draw these triangles, what's going to happen? So if we were to draw this triangle here, it would be kind of sort of something like this, where here's our angle A. A was given as 35 degrees. Here's our angle C, slightly bigger than 90 degrees. Here's our angle B, right? So if we were, that's if we were to draw this triangle here. Now the other possible triangle that we get from this initial setup was this one here, where angle B is much larger. So angle A is still the same size, just the 35 degrees, but angle B is now much larger. Okay. Okay, so here's C, A, and then here's angle B. Okay, so that's all that's going on there. So just 2 possible triangles that we get from this initial setup here. So that's one of the things that could happen with SSA. So that's why it's called the ambiguous case, is because it's ambiguous which triangle we're talking about. It's this here doesn't uniquely define one triangle. It's ambiguous because it defines two triangles. So that's example 5 with the law of sines and an example illustrating the ambiguous case. And remember just to do the inverse sine and then 180 degrees minus the inverse sine when you have the SSA triangle. Okay, so that's example 5. Example 6 coming up next.